Welcome to the second video in the Quantum Field Theory Basics series. If you're like most students, you've probably already learned something about chemistry, Newton's physics, electromagnetism, relativity, and even quantum mechanics. In this video, I'll tell how quantum field theory relates to those other theories. We'll start with the Standard Model, which I call the secret theory at the core of physics. The Standard Model is a quantum field theory with a particular set of symmetries imposed on it. The symmetries represent guesses by theoretical physicists for how the universe works. If the symmetries produce verifiable predictions, then they become physics principles. The symmetries of the Standard Model have been verified hundreds of times in countless experiments. The most famous verification was the Higgs field in 2012. Physicists are currently making guesses at other symmetries that could be added to the Standard Model. The most famous of those is called supersymmetry. These ideas are called theories beyond the Standard Model. The approach of this video is that you need to understand the current theory before speculating on future theories. The current theory is the Standard Model. For now, just know that the Standard Model is one particular quantum field theory, the one that has been verified with experimental evidence. So we start with the Standard Model as the most general theory in science. The Standard Model is required in the high-energy and high-speed world of accelerators and cosmic rays. Part of the model describes light, which always goes at the speed of light. Duh. As energy levels are reduced, the quantum part of the theory usually becomes less important, and this part of the theory reduces to Maxwell and Faraday's classical theory of electricity and magnetism. That's the wildly successful theory engineers use to design most of the gadgets we commonly use. They don't need to know quantum field theory if they ignore certain inconsistencies, like the infinite self-energy of the electron. The other side of the Standard Model relates to fields with mass, like the electron and proton fields. For this part, the Standard Model reduces to quantum mechanics, where little particles such as electrons and protons and atoms emerge from the fields. Quantum mechanics works well when you can disregard Einstein's theory of relativity, which conflicts with quantum mechanics. Quantum mechanics is quite useful for describing condensed matter and atoms. In this region, it is accurate enough, and it's much simpler than quantum field theory. When most think of physics, they're thinking of classical mechanics. It's the one taught first in school because it's the closest to everyday experience. Classical physics is very good at predicting how balls will roll down ramps or fly through the air. It is often summarized with Newton's 3 laws. The Standard Model does not directly have a notion of object or acceleration. In the Standard Model, the field and its oscillations are the thing. What's amazing is that the oscillations in the field become objects, and those objects start to look like classical objects as energy levels are reduced to everyday values. The mathematics for this is complicated, but the general flow is the Standard Model goes to quantum mechanics, goes to classical mechanics. That brings us to Einstein's theory of relativity, which has two parts, the special theory and the general theory. The special theory of relativity is built into the Standard Model. You could say that special relativity comes from the Standard Model, but really the two are almost inseparable. General relativity is a different case. It is currently our best theory for gravitation. General relativity is a field theory, but not a quantum field theory. It's a classical field theory. It can be made into a quantum field theory, but that currently doesn't have any verified predictions. Therefore, it has no advantage over the classical field theory. Remember that all sorts of cockamamie theories are possible. Only the ones that make verifiable predictions are considered to be science. Therefore, general relativity currently sits apart from the Standard Model. Many physicists would like to see them merged. As the energy levels and speeds are reduced, general relativity reduces to Newton's theory of gravitation. Newton's theory is a practical theory that is much easier to learn than general relativity. Kids in school are usually taught that Newton's theory is a law. That is not true. Newton's theory is a good approximation to Einstein's general theory of relativity. It is not a law of nature. In fact, humans have never discovered a law of nature, only approximations. The Standard Model also has a very close relationship to statistical mechanics. Remember that statistical mechanics is the theory that explains such things as pressure and temperature in gases, how lasers work, and how ovens heat up with black body radiation. Most high school students learn a subject called thermodynamics instead of statistical mechanics. Statistical mechanics provides deeper understanding of why thermodynamics works, and it's usually taught in college. Statistical mechanics assumes the world is divided into two types of things, bosons and fermions. The Standard Model is the only theory that offers an explanation for that division. The Standard Model is also the only theory that offers an explanation for identical particles, which are required for statistical mechanics to work. Statistical mechanics also has a concept of entropy, which always increases with time. That produces the arrow of time and allows us to distinguish the past from the future. The Standard Model also has an arrow of time and predicts that entropy will always increase. Classical mechanics and quantum mechanics do not have that feature. Since quantum field theory reduces to the other theories of physics as the energies are reduced, you might ask, why do I even need to know about quantum field theory? And the answer is you don't, unless you're curious. You can live your life and reproduce and be successful in the biological sense without knowing quantum field theory. The advantage of quantum field theory is that the number of rules is reduced. Let me illustrate with some chemistry. Here's a glass of water. Chemists would say that it contains hydrogen and oxygen atoms, and they have rules for how the atoms combine. They accept the existence of atoms without further questions. The Standard Model explains the existence of atoms from more basic rules. This water is from California, and here is some from Texas. Chemists accept that the molecules are the same without asking how Texas could have the same recipe for water as California. Quantum field theory explains this. The Texas water happens to be very hot, as you can see from an infrared camera. The infrared radiation that the water is giving off is known as black body radiation. Black body radiation is paradoxical in classical physics, but it is nicely explained in quantum field theory. The chemist usually doesn't think about that paradox, even though she may use rules derived from black body radiation theory. So chemists and other scientists assemble a large number of rules to help them do their jobs. The idea of quantum field theory is to explain where those rules came from and when they will stop working. Yes, quantum field theory is great, but there's a problem. It's very hard to learn. In the next video, I will try to help by clearing up some of the confusions of learning quantum field theory.